In today's video, we're going to be taking a look at the basics of electricity and the science, a little bit of behind it, the theories, and we're going to take a quick trip back into your 4th grade science class. So the atom is made up of protons, neutrons, and electrons. Does that remind you of 4th grade at all? But the only ones that we care about is the electrons. And of the electrons, the only ones we care about are the ones that are in the outer orbit, also referred to as the valence ring. So electricity is the flow of electrons, or the concentrated flow of electrons. And we're going to take a look at what does it take to make the electrons move, what will increase, decrease, or stop the flow of electrons, and how do you check the flow. So a conductor is copper, gold, aluminum. It's going to be determined by the number of electrons that are in that outer ring. So if there are 3 or less electrons in that outer ring, it's going to be a good conductor of electricity. Insulator, again, is going to be determined by that outer valence ring. If there's 5 or more electrons in that outer valence ring, then it's going to stop the flow of electrons. So that's going to be things like rubber, wood, ceramics, most plastics. So this, I'm sure, is not anything new to you. It's just an explanation as to why something's a good conductor or why something's a good insulator. Semiconductor is going to have 4 electrons. It is neither a good insulator or a good conductor, and we will talk about semiconductors in more details when we get into the electronics of it. So, electrical definitions is the flow of electrons through a conductor. And then there's 2 theories. One is the electron theory, and that says electricity flows from negative to positive. The second is conventional theory, which says electricity flows from positive to negative. Now, this is one of the few times when I'm not concerned about what the truth is here. What I'm going to always be doing is referring to electricity in conventional theory, so flowing from positive to negative, for 2 reasons. The first is if you look at the image that's right there in the center, so this top one right here, that's the symbol for a diode. A diode is like an electrical ratchet. It's going to allow current to flow one direction and block the current in the other direction. And look at the arrow, and the arrow is pointing in the direction of the current can flow. So even electronics diagrams are drawn with conventional theory. So the image right underneath that is a physical diode, and you can tell the cathode or the negative side of the diode by that stripe that's on there. The second reason is one of the best wiring diagrams that's out there is the Valley Forge style schematic, that they have power at the top, ground at the bottom, and current flows from top to bottom. So I will always refer to electricity as flowing from positive to negative. If you have a conductor, so hold a wire in your hand, that wire is already full of electrons. So you're not going to fit more electrons in there. So what's going to happen is, if you start pushing electrical pressure, one electron is going to push on the next electron, push on the next one. And to symbolize this, taking these pool balls, get them all lined up. If you take the cue ball and hit the number 1 right on the end there, the force of that impact is transferred through all of those balls, and then the number 15 ball takes off on the end. So electricity is very fast, almost the speed of light. However, the electrons move relatively slow because they're just going to push one electron to the next electron to the next electron. So here's 5 terms that you need to memorize if you're taking notes. Make sure you get these written down because you have to keep these in mind as we go through and we're talking about electricity. So everything we talked about from here out is going to be these 5 terms, and you're going to need to know them. So the first one is voltage, and the term that I want you to memorize for that is it's pressure, electrical pressure. That's what's going to push the electron. The second one is amperage, which is the flow of electrons. Third is resistance, and I'm going to refer to that as friction, or it's going to be creating heat. So fourth one is a circuit, and that's the path. Now to keep in mind, if our path is starting at a battery, it's going to end at the battery. So start at the positive post, end at the negative post. It has to be a complete path from the source back to the source. If your source is the alternator, it's got to go from the alternator back to the alternator. And the last term is a voltage drop. This is where you're going to live when you're doing most of your diagnosis, is looking at voltage drops. So you won't be using the ohm meter very often. You won't be using the amp meter very often. So don't misunderstand me. You will still use those. But the voltmeter is actually the much better one to use. So a voltage drop is an indirect measurement of resistance. And that is a large voltage drop is going to indicate a large resistance, a small voltage drop, a small resistance. So voltage is electrical pressure, or the force that causes electron movement. The other term that you'll hear for it besides voltage is electromotive force. So I typically will talk about a person who has too many years of college, and these one-syllable words don't work. So instead of calling it a volt, they call it electromotive force. But the two words are interchangeable. You can use a voltmeter when you're measuring it, when we're talking about it, to abbreviate it. So I will always abbreviate it with a V, but you'll also see it sometimes abbreviated with an E for the electromotive force. Current is how many electrons pass through one point. The term amp, again, has one syllable, so that just won't suffice. So they have to use the term intensity. So again, intensity, current, or amps, same thing. Technically, it is 6.2 billion electrons passing through 1 point in 1 second. So two things about that. First, I'd really like to meet the guy that counted those. And second, that's more of an academic term. Now, when you hear me use the term academic, what I'm talking about is if you grab a old Webster's dictionary, and this is like one from back from the 1960s, 1970s, somewhere in there, and you look up the word academic, and you go through the different definitions. As you go through there, you'll finally find one that actually says useless information. So you can work with electricity all your life, you can measure it and never know how many electrons it actually is. So again, it's going to be abbreviated with the A or the I if they're using the intensity. Resistance is the force that opposes electron flow. It's going to be measured in ohms, but the one word that I want you to remember is friction. And the reason is as electricity flows through a resistance, it's going to create heat. If there's a little bit of resistance, it's going to be just a little bit of heat. If there's a lot of resistance, it can be a lot of heat. And an incandescent light bulb is really the best indication of that. Take an incandescent light bulb, turn it on, wait a few seconds, and then grab a hold of it with your fingers. You probably won't do it a second time because it gets really hot. So an incandescent light bulb, best definition that I've heard for an incandescent light bulb is a heater that happens to give off light. And they're only about 20% efficient, meaning that 80% of the energy that they consume is heat. So there are some, when you start going to some of these advanced electrical classes, you'll find guys using an infrared camera to find resistances on a circuit because it'll show up as being warm or hot. It's going to be abbreviated with an R or the ohm symbol there. And again, resistance, that has enough syllables. They didn't need to come up with another word for that one. 5 characteristics that determine resistance. And we'll go talk about the first 4 really quick. In that copper is going to conduct electricity better than aluminum will. 2, the length of the conductor. So we have no superconductors. Everything's going to have a little bit of resistance to it. The longer the wire, the more resistance it'll have. 3rd, the diameter of the wire. A larger wire is going to have less resistance than a small diameter wire. Now, talking about that, also, if you have a multi-strand wire, because electrons like to flow on the surface of the wire. So you can have the exact same size wire that is a single strand, or like this image shows, the multi-strand. The multi-strand has more surface area, so it'll actually have less electrons. The fourth one is the temperature. Hotter it is, the more resistance it'll have. Now, those first four, that's what the engineers are looking at when they're deciding what size wire that they need to use on this particular circuit based on if it's under the hood, it's going to be hotter, so it may need a little bit larger wire than if it's under the dash. How many amps are going to flow through it? How long is it? And that's what they're going to use to figure out what size wire they need. For you as a tech, if you have to replace a wire, use the same size diameter wire or larger when you replace a section, and it'll be a good repair. The fifth one, this is where you're going to be doing your diagnosis. So again, looking down at the image on the left, you can see the copper, it's clean, it's bright, and electricity can flow across there really well. The one on the right is oxidized, meaning it's corroded. Since electrons like to flow on the surface, and the surface has become oxidized, meaning it has oxygen molecules now attached to it, it changed that conductor into an insulator, and that's going to be resistance. So when you're measuring, you find a wire that has a high voltage drop, meaning it has high resistance, and you split it open, you see it look like this, you're going to need to keep exposing the wire until it looks like it does on the left, and then replace that section to get rid of that corrosion. So the last one is the only one that you need to be concerned about, and that is the physical condition. If it's been cut, damaged, or corrosion like that, needs to be replaced. The rest of it, as long as you put the same size wire or larger when you're replacing the section. Battery down here at the bottom, nice Optima battery. The terminal on the left is our positive, the terminal on the right is our negative. Now, a fully charged battery will have 12.6 volts, and that's 12.6 volts at the positive terminal. The negative terminal is 0 volts. Hook it up to a circuit, so if this is your only source on the circuit, negative post will always be 0. No matter how much or how little current is flowing on there, negative post will always be 0. Again, if it is the only source of electricity on the circuit. Now, we're starting off with 12.6 volts or whatever voltage you start off. As the current flows through the circuit, if it comes to a little bit of resistance, there's going to be a little bit of voltage drop as it pushes the electrons through that. When you get to the load, light bulb, motor, solenoid, whatever it is, there you'll have a large voltage drop. But all the resistances on there are going to cause voltage drops as it goes through. So taking a look at where the meter is hooked up on this image down here at the bottom. Now, if I were to take that voltmeter and hook it up to the positive and negative terminals of the battery, there I'm checking my voltage source. But on this one here, what we're doing is we're actually checking the voltage drop. So when you do this, what you have to keep in mind is where you put the black lead of the meter says that's 0. Regardless of how many volts are actually there, the meter's going to say that's 0. And then where you put the red lead, the meter's going to measure the voltage difference between where the black lead is and where the red lead is. So this is how you're going to measure voltage drops. And again, since we have a high resistance right there, we should have a high voltage drop. But if you're measuring a wire, you should have a very small voltage drop. So it doesn't matter whether it has 2 ohms or 20 ohms. If it's going through a wire, you should never have more than a 200 millivolt drop as you measure across a wire. If you exceed that, there's something wrong with that wire. A loose connection, corrosion, something on there. And it needs to be fixed. So we don't need to know exactly how many ohms. All we need to know is that, hey, there's too many ohms or too much resistance, and that's where our problem is. We need to fix that. Ohm's law. takes 1 volt to push 1 amp through 1 ohm of resistance. So I found this drawing on the internet, and I don't know whose it is, but I really like this drawing that they have here. So with knowing that it takes 1 volt to push 1 amp through 1 ohm resistance, we can get a math formula for that. So if you don't like math, you're not going to like this next part. So the top triangle there shows the E over the I and the R. So the E, again, electromotive force, I, intensity, and the R, resistance. So what I'm going to be using instead of that is the exact same thing, the triangle underneath there, and that is V over A and R, or voltage over amperage and resistance. So looking on the left side here, the top one is that upper formula. So this one here coincides with that, and that one goes to there. So if we have this formula, voltage is equal to amps times resistance. If you took even intro to algebra, you should know that with this formula here, if resistance is the value that I need to know, then it's R is equal to volt divided by amps. If amps is the one that we need to know, amps is equal to volts divided by resistance. And some people can look at this image down here and they can see these formulas. For me, I look at that and no, sorry, I don't see that formula. So I just remember these 3 right here, and I know that anytime I'm going to go through and calculate or using Ohm's law, I'm going to use one of these 3 formulas. So taking a look at this example here, we have a 9-volt battery, we have 3 ohms resistance. So I have 2 of my values. Which one of these formulas am I going to use? And hopefully you said that amperage is equal to voltage divided by resistance. So I'm now going to take 9 volts divided by 3 ohms, and that tells me that on this circuit here, 3 amps are going to flow. On this one here, now I know my voltage, and I know my amperage. So the formula that I need to use is going to be the resistance divided by, is equal to voltage divided by amperage. Now, I did this one on purpose. If we go back to here, you see I have 3 ohms and 9 volts, and I end up with 3 amps. On this one here, I increased my voltage, but I still have 3 ohms, and I increased my amperage. So, increase the voltage, you will increase the current through there because you're increasing the pressure to be able to push through that. Now, the place where you have probably seen this is if you have your headlights on, drive the car, pull up to a wall or garage door or some surface where you can see the lights, and then you shut the key off and you see the lights dim down a little bit. So with the car running, you'll have about 14 volts. With the car shut off, you're down closer to 12 volts. So as you lose that 1.5, 2 volts, the lights dim down even though the resistance remained relatively unchanged. This time we know the amperage, we know the resistance. So the formula that we need to use is the top formula there, which means 4 amps times 12 ohms, and we have a 48 volt battery. So one more, and that is Watt's law. And 1 watt is also expressed as power, so you'll see the P or the power for watts. And what a watt is, it's a measurement of the work that's being done. So if you've done much with engines, you know that we're going to measure engine horsepower, which is a measurement of work that that engine can do. So if you were to go to a Volkswagen dealership website here in the United States, and you want to see how much power that engine produces, you'll look it up and you'll find, hey, it's got 200 horsepower or whatever the horsepower rating is of that engine. However, if you go to a British Volkswagen dealership and you look up the power that the engine produces, they're going to give you the number in kilowatts instead of horsepower. 746 watts equals 1 horsepower. So watts is a measurement of work that's being done. So we have the formula of power is equal to volts times amps. And again, voltage divided by power, or voltage is equal to the power, or the watts, divided by amps. And amps is equal to the wattage, or the power, divided by volts. So similar three formulas. We're not going to be using this very much, but I do want you to understand what a watt is, because you'll see it, and you have already seen it. So this one here, we have a home light bulb. It's a 60-watt light bulb, and you see they designed it to run at 130 volts. So 60 watts divided by 130 volts means it's less than a half amp, so 0.46 amps. Now on this one here, this is a high beam headlight, which is a 60-watt light bulb. So same 60-watt light bulb, but now with the car, we only have 13 volts. I chose 13 just for this demonstration instead of going with 14. So 60 watts divided by 13 volts is 4.6 amps. Now, taking a look at this. Home with 130 volts, 40.46 amps. On the car, 13 volts, 4.6. So household with 10 times the voltage, you have 1/10 the amperage. On the car, where I only have 1/10 the voltage, I have 10 times the amperage in order to be able to do the same amount of work. This is the reason that in the mid-50s, the automotive industry switched over from 6 volts to 12 volts, as they can use smaller wire, less amperage to do the same amount of work. The automotive industry has been discussing for decades going away from a 12-volt system to either a 24-volt or a 36-volt system. They never have done it, and now as we get more hybrid electric vehicles, we have our higher voltage. And you will not see an electric vehicle that the motor that's moving the car down the road is a 12-volt motor. So they're using hundreds of volts on that motor to move the car down the road because they can decrease the average. So this last one here, and this is the amplifier. This is the one that you put on the car so everybody gets to enjoy your music. Even though most people say, oh no, I'm just a purist, I want it to be a really clear sound. It's, well, yeah, okay, but you still crank it up so everybody listens to your music. So this one is an 800-watt amplifier, and we're going to run this with the car on. So 800 watts divided by 14 volts is 57 amps. Now, on your car with 120, 130 amp alternator, and you have your windshield wipers on, you have your blower motor on high, you have your seat heater on, you have the rear defogger on, and then you turn this amplifier on, you're going to exceed the output of your alternator. However, on these amplifiers like this, the only time you're ever going to draw 800 amps, or 800 watts, sorry about that, 800 watts on this, is if you have the volume cranked all the way up, and then you hit those bass notes, and it's just, so everything shakes on the car. That's where it's going to be the high amperage. It's for a short duration, and so the draw on these really isn't that high. It's just surge. Two types of electricity. We have DC and AC. So when I learned how to work on cars back in the 70s, they didn't even teach us about AC. And they said, yeah, AC exists, but they only taught us DC because that's all we had on the car was DC volts. And looking at the chart on the left, you see your DC volts. The black line going horizontal is 0 volts. So we're going to have just a positive voltage up above that. So if you were to take a lap scope, hook it up to a battery, that's what it's going to look like. That would be a good flat line going across there. Now, if you were in the hospital and they had those probes hooked up to your chest and your heartbeat looked like that would be really bad. But for a DC battery, that's good. Now, the one on the right-hand side, so 0 volts is the same, and this is AC voltage. So AC is going to alternate negative voltage, positive voltage, negative voltage, positive voltage. It's just going to go back and forth like that. Now, the difference between a negative voltage and a positive voltage is represented by those green arrows on there. So, voltage is electrical pressure. So you see on the negative, the electrical pressure is going from left to right. On the positive, the electrical pressure is going from right to left. So it's the same pressure, it's just moving back and forth. So on a DC, your electrons are going to be slowly moving through the wire in one particular direction. But on AC, the electrons go one direction, stop, go the other direction, stop, go back to the other direction, just alternate back and forth like that. So that's your AC and DC. And now we have wheel speed sensors, which most of those are still alternating current. We have other sensors on the car that use AC. And now that we have more hybrid electric vehicles, those are using three-phase AC voltage. So you have to understand both AC and DC. So that brings us to the end of this one. And we'll have our next video on series circuits.